All right, hello everyone. This is Emily Comacher, and I chose to do my screencast over fractal geometry. And now fractals occur not only in geometry but also in nature and in algebra as well. It was kind of inspired by the fractals that occur in nature, so we're going to look at all three of these areas as we go through this screencast. So, starting in nature and what it means to be a fractal. Fractals come from the Latin verb which means to break, and it occurs in many places in nature. So, starting by looking at this fern here, you would recognize a fractal as kind of like looking at each individual part of this fern, like the branch of one of these branches of the fern, and seeing how this branch kind of represents or is similar to the fern as a whole. Now, looking even closer than that, each little leaf on this branch also will represent the fern as a whole. So, kind of zooming in on this fern, you see that kind of, they call it self-similarity concept, where every portion is similar to what the whole looks like. Okay, you can see that kind of in this branch of broccoli here, where each of these individual knobs kind of resembles what the broccoli looks like as a whole, or any one of these plants or flowers. If you zoom in on one of these flowers, it looks and resembles the whole set of flowers as a whole. Now, formulas can be assigned to these objects that occur in nature, like the fractals that occur in a tree. So, like the trunk and the branches and the stems, how they kind of all branch out at the same pattern, at the same fractal pattern. That can lead scientists to come up with all sorts of conclusions and help them. So, for example, a group of scientists were able to then, from this formula pattern for the fractals that occur in a tree, they were able to look at an entire forest of trees and determine the amount of carbon dioxide that a whole forest collected and help them draw conclusions about global warming that affects us today. So that was kind of an exciting new avenue that fractals allowed them to explore and to study, was, things that are affecting us today, even like global warming. So where this was first inspired was by a man by the name of Benoit Mandelbrot, who was born in Poland on November 20th of 1924, and he was kind of the father of fractals. He kind of discovered them. He found an interest in the patterns in nature and saw them as just more than random coincidence. And that led him to, really studying these fractals. He once said, "Think not of what you see, but what it took to produce what you see," which I think is kind of an in-depth and very it really tells what fractals are about. It's producing what you see, and there's a lot of what you see, what you can't even see with the naked eye, in fractals, that you kind of just have to zoom in on, and this is very much describing what fractals are all about. So, fractals, when it comes to geometry, things are studied like the Sierpinski triangle, for example. So this Sierpinski triangle is an example of a fractal that occurs in geometry, where you just start with one equilateral triangle, like here over here in the black, and then you find the midpoints of each one of those sides of the equilateral triangle and form a new triangle, where you kind of subtract that area out. So that's in the white, and then each one of the three remaining triangles, you repeat that process again, and until you have 9 triangles then, and then you repeat that process again, and then subtract out those triangles, and you do it again and again and again and again, and you then come up with an infinite set where you're subtracting out those areas, and it gets to the point where what you can see, maybe you can't even see a layer that's closer than this, but if you keep zooming in further and further and further, the object will appear the same as what the original object did. So no matter how far you zoom, it has that self-similarity concept, where the zoomed in image resembles what the whole image looked like. So another example of this geometric fractal is the Van Gogh curve, where you start with just a straight line, which I didn't include, but you start with a straight line and then you segment it off into thirds. So this would be 1/3, the third that I've subtracted out, and then the third that is here. And then we take that middle third out, and we extend and make kind of a triangle on top of that, where each one of these 4 segments is the same length. So this length would have to be the same as each one of the four, and then you do that process again. So each one of these individual four lengths is separated into thirds where that middle piece is cut out, and then that triangular pattern is displayed over top of that. And then you do it again and again and again and again until you can no longer really even tell that it's being done. But if you would zoom in and zoom in and zoom in closer, you would see that fractal pattern going on where the part looks the same as the whole. So here's an example of a Van Gogh snowflake. It's hard to even see the difference between this snowflake and this one, but if you zoom in closer and closer, you'll see that it does have an extra layer of that pattern going on. So very, very interesting. There's a ton more geometric fractals that occur, people doing different geometric patterns that are all very beautiful. And in geometry, there's these patterns going on with many different shapes. So moving into the algebra side of things, the algebra side of fractals, there's a man by the name of Gaston Julia who started studying fractals and was inspired by Mandelbrot to really bring fractals into the algebra world. So he started looking at something that he coined the Julia set. So for example, the Julia set would have this common principle. So let's say you start with a function like x squared plus 1 equals y. You would have to first plug a number in for x, like let's say 1, okay? So if we plug 1 in, we would do 1 squared plus 1, which is 2, so our y value would be 2. Then you would take that output value and plug it back in for the input value. So 2 would go in here, 2 squared plus 1 is 5, so 5 would be your new output value, and then you would plug 5 back in as your input. And you would repeat this process where the outputs become the inputs, and you would get a new output, and you would repeat that process over and over and over again until you got a set, and then you would plot that data set. Okay, so what he decided to do, what Julia decided to do was kind of an equation that resembles that x squared plus 1 pattern, except it's written in this form where z of n minus 1 or the c value are representing complex numbers in the form of a plus bi. And he would try different complex numbers in for each one of those variables, and then he would plot them on the complex plane according to, he would assign different colors according to how fast this data set with those complex numbers plugged in, according to how fast it diverged, if at all. So, each one of these Julia sets represents a different function or a different complex number plugged in to his formula here, and colors are assigned to those values in the complex plane to represent diverging sets. So very, very beautiful graphs here. And again, if you zoom in on each one of these and zoom in forever and ever and ever, it will continue to represent that self-similarity concept of what the parts look like as a whole. Okay, so Mandelbrot then kind of took the reins back again and was inspired by Gaston Julia's discovery of this, and he wanted to make one set that combined all of these Julia sets together. And so this is the Mandelbrot set, which kind of takes into consider all of the Julia sets, and this has kind of become the emblem for fractal geometry. So if you look up fractal geometry, a lot of times run into the Mandelbrot set somewhere. So now, extending this to science and how it's related into the real world, scientists have now started to use, other than the tree example that I used before, kidneys, lungs, heart rhythms have fractal patterns, dynamics of the brain, and then blood vessels throughout our bodies. I found something interesting that said, here might be an example of what a blood vessel looks like maybe in the kidneys, what a set of blood vessels look like through our body in the kidneys. And what scientists have started to use fractals to do is to diagnose cancer early. So here's maybe a set of blood vessels that is wrapped around a cancerous tumor, and maybe this cancerous tumor is so small that it can go undetected by ultrasound, but what ultrasound will detect is the flow through these blood vessels. And a man by the name of Peter Burns, used this to his advantage. He's from the University of Toronto, and he started to study the blood flow through these blood vessels that was able to be detected under ultrasound. And he found that blood flow through blood vessels that were wrapped around a cancerous tumor have a very, very different fractal pattern than what cancer-free blood vessels had. So very interesting that they're using this fractal geometry and fractal patterns to, to diagnose cancer and to look at carbon dioxide in, forests and things like that. It's very interesting. So that's my study on fractal geometry. It's much broader of a concept. So if you ever get a chance to study it further, it's very, very interesting. So